This is the online blackbody spectrum simulation that students will use to complete the blackbody radiation data collection and processing activity that is found on the student Google site. The purpose of this data collection and processing activity is broken into two parts. In the first part, students will manipulate the temperature within this blackbody spectrum simulation and see how an increase and decrease in temperature relates to the change in intensity of the blackbody spectrum curve. In the second part of this investigation, or the second part of this data collection and processing activity, students will use the relationship between intensity and temperature, manipulate the relationship between intensity and temperature, and attempt to calculate the Stefan-Boltzmann constant, which is 5 times 10 to the minus 8 watts per meter squared Kelvin to the 4. The concept of blackbody materials occurs in 3 units of the IB physics curriculum. That's in the quantum physics unit, the nuclear physics and quantum physics unit, the climate change, and the optional unit of astrophysics. In my experience, students have had difficulties understanding what a blackbody is, and have had a difficulty relating to the Stefan-Boltzmann constant. Therefore, by completing this data collection and processing activity, students get a hands-on experience of the direct relationship between temperature and intensity and start to understand the importance of this constant. At the start of the student video that is attached to the student Google site, I've attempted to give a brief introduction of what a blackbody absorber, a blackbody emitter, and what this blackbody spectrum shows. However, it's only a short 7-minute video, and you might find that before students undertake this data collection and processing activity, students might need some additional help from their teacher to help understand really what's going on when we're talking about theoretical black bodies. However, in this simulation, as I said before, students are asked to manipulate the temperature. Now, before students actually carry out this activity, I spend a little bit of time showing that as we decrease the temperature, we can see that the intensity of the curve reduces, but also the peak of the intensity moves towards the red part of the visible spectrum. And if you look at the star in the top of the screen, you can see that at lower temperatures the star starts to go down to reddish colors, and at a low enough temperature will eventually go black. If we start to increase the temperature will start to move up and across, and will start to go through to the blue-violet side of the visible spectrum, and you can see that the star at the top starts to turn to a light blue color. So as we increase temperature, we increase the color output, and that's basically the same as the Hertzsprung-Russell diagram, which also complements the astrophysics, the optional astrophysics unit. When students are asked to manipulate the temperature inside this data collection and processing activity, the slide is too sensitive. So I asked students to start at a temperature of 3000 Kelvin. At 3000 Kelvin, the temperature or the peak of the blackbody spectrum curve just starts to appear. The maximum temperature I asked students to go up to is 6000 Kelvin. At 6000 Kelvin, you'll see that the peak of the blackbody spectrum is at 100 megawatts per meter squared. Therefore, it's at the full deflection of the intensity, of the y-axis intensity. We can obviously go higher than this, but going higher than this means that we go above the maximum value for intensity and can't measure the intensity correctly. So 6000 is the maximum temperature that students are asked to record, and students are asked to collect intensity measurements at every 250 Kelvin interval, so 3250, 3500, etc., etc. Therefore, you'd expect the possible error for all temperature measurements to be plus or minus 1 Kelvin. Recording intensity is not as easy as taking the temperature, and for this we're going to need to use the ruler. If we select the ruler and we move the ruler to to measure the height of the peak, you can see that the peak height is at 29 centimeters. At 29 centimeters, this is 100 megawatts per meter squared. Therefore, 1 centimeter of the ruler equals approximately 3.5 megawatts per meter squared. So if we then enter a value, for example, of 3,500, and we move the ruler again, we can take a measurement of about 2 centimeters, and therefore at 2 centimeters we expect an intensity of 7 megawatts per meter squared. Students are given this information in the video on the Google site, but this information is also included in the black body radiation data collection and processing instruction sheet that can be found on the Google site, on the student Google site and the teacher Google site. Obviously, the error for this intensity is going to be half a centimeter. I can measure to a height of 1 centimeter, so half of 1 centimeter is half a centimeter. So we'd expect an intensity possible error of 1.8 megawatts per meter squared. The reusability of this object, this learning object or this simulation is very good to collect data and to construct the Stefan Boltzmann's constant, but it's also very good for the Wien's displacement constant, which is also needed inside the astrophysics unit. For this, we're going to look at the relationship between wavelength and temperature. All we need to do this data collection, all we need to do to find this constant is to change the wavelength axis, and then to try and find, or to try and take measurements of where the peak lies to the wavelength for given temperatures. This is not part of the data collection and processing activity that's found on the student Google site, and this would be an additional data collection and processing activity that you could do yourself if you wanted to use this simulation again. However, this is a very, very good simulation for to understand black body spectrums, and I value it greatly. Thank you very much.